Professor Cheryl Praeger has transformed our understanding of groups acting on large systems, producing new theories, algorithms, and designs that have advanced every field that exploits the symmetry of large systems. Her research has led to significant new directions taken up by mathematicians internationally. Her algorithms have enhanced powerful computer algebra systems which have transformed research and teaching of algebra. Professor Praeger, congratulations, and I invite you to present to us on the topic of symmetry.
Thank you very much, Professor Jagadish and Professor Corey. I'm very honoured, I feel very honoured to be awarded the Lyle Medal of the Academy, and very privileged to talk to you about my passion, the mathematics of symmetry. Symmetry is all around us at every scale, from the vast spiral galaxies that Ken told us about earlier today, through to the tiniest spiral shell. In nature and also in the built environment, we see beautiful symmetry in architecture and in other areas of science. Francis Crick and James Watson, in describing the symmetry of biological organisms, decided that it was a matter of genetic economy, so that a very small amount of genetic information, together with the symmetry of the structures, could help in replication. And in physics, symmetry lies at the heart. Quoting Nobel laureate P.W. Anderson, it's only slightly overstating the case to say that physics is the study of symmetry. In information technology, symmetric or large balanced networks help in storage, retrieval, and searches of large data sets, such as in the internet. But of course, in mathematics, we also study symmetry, and we measure symmetry via structures called groups. And they're used to study symmetrical structures of all kinds. The symmetry group of a structure is the collection of all of its symmetries. For example, take a circle, it's invariant under rotations by every possible angle, and invariant under reflections through every axis through the centre. And if you put all of those rotations and reflections together, you get its symmetry group. It's an infinite group, a huge group. And group theory is the mathematical study of symmetry. Groups might be quite small, not as big as the group of the circle. They might be complicated, they might be simple, and as a very small example, consider the group of symmetries of the square. The square's got 8 symmetries, and they're generated by 2 fundamental ones, a reflection 90 degrees clockwise through the centre, and a rotation through 90 degrees, and a reflection in the vertical axis. And if we were to put a letter F in the, how does this work? In the centre of this square, then the 8 different operations would transform the way that F would appear into the different ones that I've described here in this diagram here. Only those 8, no matter how you combine together the fundamental symmetry. And in any class of symmetric structures, different structures will be characterised by their groups. So we would regard, say, all squares as being the same. We don't care how big they are, that's just their matter of being square, their squareness. And if we looked at the class of polygons, n-gons with a different number of sides, then the different values of the number n will correspond to different groups, and so essentially different structures will correspond to different symmetry groups. And it's quite amazing how restrictive the symmetry is on a lot of structures. For example, there are exactly 7 different kinds of wall freezes corresponding to 7 different kinds of freeze groups, and here is a picture of one of them. Throughout history, mathematical theory has developed to solve the important problems of the time. In the 19th century, the problems were of, say, maritime navigation, military requirements, and new theories of electricity and magnetism to be explored. There were many equations to be solved, and that wasn't a new problem, but in 1831, the very young French genius mathematician Évariste Galois, he was the first to understand that the algebraic solution of an equation was governed by the structure of a symmetry group related to the equation. And this was the birth of the theory of permutation groups, or groups in action. By the late 20th century, the theory of finite groups focused on the building blocks for finite groups, the so-called finite simple groups. These you can think of as the atoms of symmetry, and indeed these atoms of symmetry were classified. The announcement was roughly 1980, with a few tails to be tied up over the next 20 years. In awarding the 2008 Abel Prize, the prize was awarded to two of the champions in this classification, John Thompson and Jacques Tietz. The citation referred to this classification as one of the greatest achievements of 20th century mathematics. And we can represent the finite simple groups in a type of periodic table similar to the periodic table used to represent the chemical elements. The finite number of columns in the table represent different infinite families of finite simple groups. And down the bottom, there's a few that don't fit into any infinite families, in fact, exactly 26 of the so-called sporadic groups. And so to the 21st century. We want to harness and exploit the immensely powerful simple group classification to study symmetric structures. And we also want to take full advantage of fast digital computation. Major advances inevitably require new fundamental theory, in particular to develop and to apply detailed knowledge of the simple groups. I will try to illustrate by mentioning three research directions I've been involved with, both fundamental new group theory and new applications to networks and algorithms. So what is needed to exploit the simple groups? So just naming them is not sufficient to have a full understanding of their structure, enough to use them to solve other problems. Even simply stated problems like the ones below that I'll talk about, they remain largely unsolved. So the simple groups actually have quite a complicated structure internally. They're defined as being simple by having no normal subgroups, but they certainly have lots of other non-normal subgroups. So what do all of the largest, the maximal subgroups of the simple groups look like? In what ways can we represent the simple groups compactly, say as groups of matrices or groups of permutations? And what elements would be obtained frequently if we were to make random selections from a simple group, and indeed from any group? Solving many problems requires the simple group classification, and new advances are needed to make the current theory fit for each new application. Knowledge of the simple group structure and representations, as I said, is still incomplete, and this challenge continues to engage me and other researchers around the world. The answers are critical for applying the classification to group actions on symmetrical structures and for efficient computation with simple groups. Here's the first one I'd like to explain. The alternating groups are one of the infinite families of finite simple groups. These are the groups of even permutations of, say, AN, a set of size n. The alternating groups are the yellow column on the left-hand side of the periodic table, and the smallest non-abelian simple group amongst that family is A5, and it was the simple symmetry group of the cowpea mosaic virus that I showed you earlier. In 1990, roughly 10 years after the announcement of the classification of simple groups, two colleagues, Martin Liebeck and Jan Saxel and I, reduced the problem of classifying the maximal subgroups of these alternating groups to another problem. which was a problem about all simple groups, namely the one in red, classify all the ways that you can factorise any simple group S as a product A times B, where A and B are maximal subgroups of S. Now, we managed to solve this problem in red. It was quite complicated. The solution occupies a research monograph, and it's my most highly cited publication because it's very, very useful in all sorts of other applications. The next one. I'd like to talk about edge-transitive graphs. These are networks where all of the edges, that's the links, are equivalent under symmetries of the graphs. There's some very beautiful ones, and I've shown here one, the Shrikanda graph. They're very beautiful, well-balanced networks. But the problem is to gain an understanding of the essential structure of graphs in various important infinite families of these edge-transitive graphs. I introduced a special quotienting method called normal quotienting, and I'd like to tell you what I mean by quotienting a graph. So you take a graph, say that one, you partition the vertices into a few sets, and then to take the quotient, you merge all the vertices in each part to a single vertex, and where you see some edges, you put an edge, and if you don't see any edges, you don't. And so you get a smaller graph, the quotient graph. And it's a bit like viewing the graph from a long way off through a telescope so that some of the details disappear and you just get to see the essential features. The trick is to do this while preserving the symmetry that you care about. And my contribution was to take a particular method of taking these quotients called normal quotient construction, which replaces very complicated graphs by smaller basic graphs, which have at least the same amount of symmetry and a bit more. And then the problem is to describe the possible structures of these basic graphs to try to understand the family we're studying. The extra symmetry property that very often arose was something which was termed being quasi-primitive on the vertices of the graph. Now, these quasi-primitive groups, I won't explain exactly what they are, but they were a larger family of groups than the primitive groups, which was the very well-studied groups at the time. And nothing was actually known about the quasi-primitive groups because they hadn't seemed to be important before. So my contribution was a new theory of quasi-primitive groups, analogous to the primitive group theory, and applying this theory along with the finite symbol group classification to describe the basic graph successfully in several families of graphs. And this has become a very useful technique in studying large families of networks. Final example I'd like to mention is symmetry in digital computation. Mathematicians were present at the cutting edge of digital computation from the very beginning, and certainly this also included the group theorists. There's now two major systems, Magma in Sydney and GAP, managed in a distributed way internationally. I became properly engaged around about 1988. There was a difficult problem at the time, which was computing with groups of matrices. These groups were huge, far too big to sort of list the elements and have a look at them. And the particular problem that I was asked to address was how to recognise the special linear groups. So the groups were made up of these matrices, square matrices, which you could multiply together to get a group, and these are matrices with determinant 1. The special linear group could easily be given by just two n by n matrices with entries we were looking at in a finite field, so that was a finite group. The problem was to decide if you were given two matrices, whether in fact they did generate the full special linear group or not. This was a sort of a problem that was affecting progress. And the result over a couple of years was the Neumann-Praeger algorithm, that's Peter Neumann, and it was the first one to use consequences of the simple group classification together with randomisation to obtain a good solution theoretically, and it worked very well in practice. And this launched a full-scale international program for producing algorithms for efficient matrix group computation. I just want to say a little bit about what made it work. There were two special kinds of matrices that we identified in the special linear group, and these had two properties. If a group, that the group generated by these two matrices A and B, contained a matrix of each kind, then we had a very deep theorem that we proved using the finite simple group classification, which said that the group had to be the special linear group. The other property was that within the special linear group, there's a relatively high, reasonably high proportion of each, so that you could easily find such matrices by random selection. So that the algorithm was essentially saying, if you take enough random selections and the group is a special linear group, with a high probability you'll find one of each matrix, and you can apply this deep theorem without doing any further tests and deduce that you have the special linear group. And this was the first and rather different sort of algorithm that arose. So the modern study of symmetry of huge finite structures exploits powerful algebraic theory, including the finite simple group classification. It bridges across many areas of mathematics, network theory, computer science, statistics, etc. It makes use of large-scale digital computation, and it's always attacking new problems both within and beyond mathematics. Thank you.
Are there any questions or comments? So, Cheryl, when you're trying to simplify your vertices, and so do you lose some of the information, or you're...
In the networks?
Yeah, networks. Yeah.
Yes, you do lose some of the information, but what you're trying to do is get at some essential information. So you try to, through this normal quotient method, you do keep track of how the original graph is related to the quotient. And so the first job, and first difficult job, is to describe the basic ones. Yeah.
Any further questions or comments? If not, could you please join me to thank Professor Praeger for the interesting talk?